Okay. So from today we start the last leg of this course, and in this last leg what we will be talking about is rather an advanced topic. Yes.
Sir, can I ask one thing
There is
before you?
a echo. There is a echo. Sorry.
Hello, sir. Can I ask one thing before you start?
Yeah.
Yeah. Sir, what is the deadline of submitting the outline that you have said what previously?
Uh, the deadline for submitting the outline as soon as possible. So
Okay.
let's say by next week.
Okay, by the end of the next week. Is that
Yeah, we can keep it on next Friday.
okay, sir? Okay.
Okay, so in this last leg, what we will be doing is to deal with something that is normally not so much considered in a superconductor, and that is phase fluctuations and related effects. Okay, so what do I mean by phase fluctuations? When we read VCS theory, we started, of course, with a VCS wave function, which was of this form. Wait a minute, this one note has hanged. Let me close it and restart it. Okay, we started with a wave function like this. And then we went ahead and found out what is u and v variationally, and then we also solved the problem through canonical transformation. But what we also pointed out is that actually when we write like this, it's not the most general form. And in the most general form, we also have to consider a phase factor, and that is a phase factor that comes here as e to the power, I think I had used theta, so let me use I theta k. And in fact, this I theta k comes from the phase of the electrons. So if you want, you don't have C minus K dagger and Ck dagger, but you have rather, they have a phase factor. Which is of this kind. Now we also showed variationally that at least for the ground state, theta k is independent of k. And if you remember the derivation, we did that for the ground state. But then when we went and solved the finite temperature properties, when we did the excited state, we did not bother about theta k anymore. Now this part, not bothering about theta k, is an approximation that BCS had done. What they had assumed is that you get into a phase coherent state at t equal to 0. This you show it rigorously. And then you assume that the state will remain phase coherent at higher temperature. Now this part you have to remember is an assumption. Why should the phase remain coherent at higher temperature? Because just like your BCS ground state has all electrons that have become paired, but when you go to a higher temperature, you have an equilibrium which is given by the thermodynamic statistics, which is that some of the part of the electrons are in the excited state, so you form Bogoliubov excitation by breaking the Cooper pairs. So in a similar fashion, you think that when you increase temperature, you will also excite phase fluctuation, which means that if I represent the phase by arrows like this, okay, I am representing the phase as arrows like this, so the angle that it makes with some reference arrow here, this angle is the phase. So if everything was phase coherent before, why can't I generate excitations? Excitations, for example, like phase waves, which will be similar to phonons, lattice waves, or spin-on, the magnetization spin wave that I have in a ferromagnet. So similarly, I should be able to excite, let's say, small distortions, slow distortions of the phase like this. It can have long wavelength spatiotemporal variation. And actually, we know that the phase is a degree of freedom that has a continuous symmetry. So if it has a continuous symmetry, then I can excite these phase modes, let's say very long wavelength phase modes with very low energies, with zero energy. So this is what is called Goldstone mode. And therefore, I should always excite this phase mode. So how did VCS get away without considering the long wavelength excitations of the phase. And in spite of that, why is BCS theory so successful? So the real question is that why is BCS theory so successful despite ignoring its fluctuations? Okay, so the point is the fact that VCS theory is a spectacularly successful theory for a large variety of superconductors is something that is undeniable. But what is not clear is why does it work? Because you are completely neglecting a degree of freedom. And not only you are completely neglecting a degree of freedom, which is the phase, but you are ignoring a degree of freedom that is not gap. So suppose, as I have mentioned to you before, if you had to excite the amplitude oscillation, then that's excitation that requires a finite threshold energy. But the phase excitation is breaking a continuous symmetry. So this one is something that you can excite with infinitesimally small energy. Even then, why is it that you can get away by neglecting it? So this is the first question that we will ask. And as you will see as we get along is that you can get away sometimes, but you cannot always get away by ignoring the phase. Okay. So for this, the first thing that we have to think about and we have to understand are energy scales. We know that the pairing energy scale is the superconducting energy gap delta, or rather 2 delta. So if you want that if I excite, let's say, the system to a characteristic temperature of the order of 2 delta, or if I excite with a photon, let's say, with the energy 2 delta, I will break the Cooper pair. And this is why actually your TC within BCS theory is proportional to delta. Now, by the same token, the first thing we have to ask ourselves is that what is the energy scale associated with phase fluctuations? Okay. Now, before I proceed, there is one confusion I'd like to first remove. There is already one phase-driven effect that we have studied in this course, and that is phase splits in nanowatts. Now, remember what we had considered. So phase slip in nanowire is of course a phase driven effect, but that's a fluctuation, that's a local fluctuation which is something that excites the phase over a complete rotation 2 pi. This is not the phase fluctuation that we are considering here. That was a very special case. That the phase slip happens in one dimension, and at higher dimension it's far too expensive, as you can easily show by doing the energetics. So here what we are on the other hand considering, that if I have the phase which is slowly twisted, I am not making one complete phase slip, I am not flipping the phase by 2 pi, but let's say spatially the phase gradually is was pointing in this direction, then it is pointing in this direction. So the phase is slowly changing with some characteristic wavelength maybe. What's the energy cost associated with that? So for that, we need to start with Josephson relation, actually with Ginzburg-Landau theory. So ideally, what we should have done is the BCS Hamiltonian with the phase inbuilt, we should self-consistently solve it, taking into account both the phase fluctuation and the repairing. Unfortunately, that problem is still an unsolved problem. It's a problem that is theoretically just too difficult to solve. So we will take a simpler route. What is that simpler route? The simpler route is that BCS solved the problem by assuming that the phase fluctuation does not exist. Now we will take the other route. We will assume that depairing does not exist. So that means we are at low enough temperature where the temperature that we are dealing with at the moment is much smaller than delta by Kb. So there is not much of depairing. And if I freeze depairing, then what's the energy cost associated with phase? Now remember, these are approximations because I cannot do anything better. There is obviously in such system the phase sector and the quasi-particle sector, the depairing sector, would be coupled to each other, could get coupled to each other. There is no way I can ensure a priori that they are not coupled. But since I cannot solve the complete coupled problem, I am decoupling them. Now I am pretending that there is no depairing, and I want to find out the energy cost associated with a gradient of the phase. Okay, for that, let's go back to Ginzburg-Landau. And I know that the supercurrent is given by the expression okay, for the moment I assume no magnetic field. So I take A equal to 0, which in other words would mean that Vs, so I can write this as Ns EVs, which we have been doing throughout. So Vs would be H cross by M star into grad theta. Okay, so this is what by now I know, that if there is no magnetic field, a current in a superconductor is associated with the gradient of the phase. So I have a phase coherent system, but if I apply a current through a superconductor, then of course the phase has to twist. All right. So if then there is a twist in phase, there will be a kinetic energy associated with it. And therefore, the kinetic energy will be half, what did I write? 1 by 4. Okay, let me write, then we'll see. Half phi naught, sorry, phi naught square, then m star Vs square. Okay, then this I know if I define my Ns as the electron density in the superfluid as opposed to the Cooper pair density, then I will have a Ns by 2. So that means I will have, let's say, 1/4 Ns m star Vs square and that will give me h cut square ns h cut square ns by
Sir, one thing, the psi that you have written here, is this the BCS psi?
which high that we are talking is Ginzburg-Landau. We are doing now. We are solving this problem in Ginzburg-Landau.
Okay, yeah.
BCS psi is what? BCS psi. Okay, I never write BCS psi like this. BCS psi, you mean this?
Yeah. I just want to confirm that whether it's an inner product square or not.
This is the gain. See, when we are doing phase fluctuation, we will be doing within Ginzburg-Landau. So doing it within BCS is not possible, and this is something that we have to do within Ginzburg-Landau. So doing this within BCS is something that is still a research problem. If you can start with that Hamiltonian and solve the phase fluctuation problem within BCS, that means taking both the fermionic degree of freedom and the phase, then that is something that would be spectacular. Lots of people have tried that and are still trying. Not that it will not be possible. So if you want,
Okay,
you
sir.
can try.
So as you have written here, the psi as an Ginzburg-Landau wave function or Ginzburg-Landau order parameter. That's why the half factor comes because we are treating it as an electrons order parameter.
The half factor.
The extra half factor. The extra half factor.
Half factor comes because psi naught square is the Cooper pair density. And
Okay.
I am defining Ns
NS, super electron
just
density. Okay.
super electron density. It's just a matter of definition.
Yeah.
I could have, if I defined here as Ns star, then I don't need to put the half. Ns star is actually Ns by 2. This is a trivial matter of definition. Okay, now if this is the kinetic energy, I can then write the Hamiltonian, at least the classical Hamiltonian, for phase fluctuation. So if I have phase fluctuation, that means, okay, what do I mean by that? I am not applying a deliberate current anywhere. I am not applying a current by hand. But I have phase fluctuation, which means that suppose this is my superconductor and fluctuations of course by definitions are random. So therefore sometimes the gradient will be in this direction, sometimes the gradient will be in this direction, sometimes the gradient will be in this direction, and so on. The gradient directions will be random, which means that locally there will be currents flowing, supercurrents flowing. They will not dissipate because they are supercurrent, but locally there are supercurrents flowing, but the overall net current is zero. But if locally supercurrents are flowing, then the superfluid has local kinetic energy, and the sum total of that kinetic energy will give me the Hamiltonian of the system. So this is the phase only Hamiltonian. Remember, when I am saying Hamiltonian, here I am completely ignoring that I had these two electrons which have formed a Cooper pair. I am just starting with the premise that I have this object called Cooper pair and they are in a phase coherent state. Just like BCS had started with the premise that I have just Cooper pairs and the phase coherence is guaranteed no matter at what temperature I am. Here I am assuming that the pairing is guaranteed no matter at what temperature I am, and I am just making the phase only Hamiltonian. Okay, so then I have to just write, I have to integrate this over the volume of the superconductor. Let me not write it like this. The prefactor I will take it out. So let me take out the half into h cut square ns by 4m, not m star, that is why another 4 has come, and d cube r. Alright, that is the Hamiltonian of the system. The phase only Hamiltonian of the system. Now I can, if I am at low enough a temperature, I am not close to Tc, of course this phase only Hamiltonian for a superconductor has no meaning, because there I will have a lot of Cooper pair breaking into individual electrons and Mogoley bonds. But if I am at low enough a temperature, now what is low enough we will see later on. Those are matters that you have to apply certain judgment based on specific situation. But if I am at low enough a temperature, then I can use this to look at only the phase fluctuation effect. Alright. Now there is a catch here. The catch here is that if you look, now I want an energy scale. For the bearing energy scale, I had delta. Here, what is the energy scale? If you look at this quantity over here, this is not an energy scale. The dimension is energy by length. Why? Because you know h cross square k square by 2m would have been energy. K is 1 by length, but instead of k square here I have ns. Ns is superfluid density, so it's per unit volume, which has 1 extra length. So that means that this prefactor has to be multiplied by some length in order to get the characteristic energy scale for phase fluctuation. What is that? What is that length scale? So let us go step by step. First, let us consider, okay, I could have, we will take up superconductors at different dimensions, 2 dimensions, 3 dimensions. So I could have started also with 1 dimension, but 1 dimension is not important because in one dimension you have so much of phase splits that this long wavelength phase fluctuation is actually not a very significant factor in one dimension, in nanowatts. So we will start with two dimension, which is thin films. 2D, and 2D implies that, of course, you have thin films, but not any thin films which the thickness is smaller and preferably much smaller than the coherence length. The coherence length at zero temperature. Okay, now in this case you can see that if I had a thin film like this, the thickness is smaller than the coherence length, then I can have a lot of phase fluctuations here. I can twist the phase like this, but I cannot twist the phase along this z direction. So along z I will not be able to twist the phase because the minimum length scale over which the order parameter of a superconductor can change is the coherence length. And since the thickness is already so small, I will not be able to twist the phase in the z direction, which means that I can integrate over z. So in two dimension, the phase only Hamiltonian will simplify. Oops. So this is T. And then I have integrated out this z degree of freedom, the d square r, which is on the in the plane of the film. So now I am very good because this stuff is dimensionless. And this is energy. So I have gotten the characteristic energy scale. This is what is defined as the superfluid stiffness. So actually superfluid stiffness means it is a superfluid phase stiffness. And that superfluid phase stiffness is often denoted as J. Some people, actually the experimentalists like to define it as J. The theorists like to define superfluid stiffness with another symbol, rho. Now theorists, why do we do certain things, it's difficult to understand because rho is resistivity and you get confused all the time between whether they are referring to resistivity or stiffness. Okay, we will go ahead with J. All right. So this is in two dimensions. Now, BCS, of course, when they formulated their theory at that time not so much thinking of two dimensions. It was the beginning of superconductivity. So first you have to understand superconductivity in bulk. So therefore, Their aim was rather to understand superconductivity in 3D. So what is the superfluid stiffness in 3D? In 3D, that means in macroscopic bulk samples. Now here we have a bit of a difficulty, because you see that I have a phase only Hamiltonian again, where I am not sure on what length scale to multiply with. So I have to apply some physical arguments. I have to apply some physical arguments, and even if I cannot get the exact value of the superfluid stiffness, I can get a bound. Let's say I can get, what's the lowest value of the superfluid stiffness that I can get? So if that value happens to be much larger than the gap, then of course it's an irrelevant energy scale. Very large energy scales I will never excite. So what's important for me to know is the lower bound. So in 3D, we can try to estimate the lower bound of the superfluid stiffness. And the lower bound, as it so happens that in the argument that I will be giving you is a lower bound argument, but this stiffness value that we get here is not very different from the actual stiffness value that you measure. Okay, for this you have to understand that if I take a superconductor, a bulk 3D superconductor, not a film now, then what is the minimum length scale over which I can actually apply a reasonable phase twist? That characteristic length scale, of course, would be of the order of the coherence length. Means, as I know, if I am much smaller than the coherence length, I cannot apply a twist. Of course, I can have twists that are at length scales which are much larger than the coherence length. But that will not help me in getting the lower bound. So therefore, what I will do is that I will take the superfluid stiffness in 3D as this prefactor here multiplied by the coherence length. So this is the definition of the superfluid stiffness in 3D. Very good. This is the definition, but now I have to get some numbers, because I need to understand why BCS theory works. So therefore, I will...
Sir, can you explain the thing again?
What do you want me to explain?
For the 3D case, why this is the coherence length?
Because the
This
smallest length scale. So if you want this in this integral, what is the smaller length scale cutoff? The small length scale cutoff will essentially be the coherence length. Smaller than the coherence length, I cannot apply a significant gradient to the phase. So therefore, this is the characteristic small length scale cutoff. Now, as I told you, I can of course excite phase fluctuation at larger length scales. But larger length scales fluctuations will give me larger value of J3D, because I will be putting, let's say, a much larger value here, and that will not help me in getting the lower bound of the stiffness.
okay.
All right?
Okay.
So now what I will do is that I will use the expression Okay. Okay. Using CGS units. Surajit, if you are here, we have to change all these CGS units to SI units. So 4 pi ns E star squared. So now you can plug this in the expression of J3D, and what you will get is H cross C whole square divided by 4 pi lambda L square. No, so let me, that will be with E star. So if I put, instead of E star, if I put E now, then it is 16 pi lambda L E square. Okay. This is an expression. Before the next class, I want you guys to calculate. So calculate this energy scale. For let's say niobium, you can get the lambda values from the book. You can take any of the book. I think Kittel has it, Tinkham also might have it, or in Wikipedia. So typical niobium, lead, tin, take any of these typical superconductors and put the values that you have in books and calculate what this J3D is. I will just give you the order of magnitude estimate. If you put in these numbers, you will see that J3D by the Boltzmann constant will be 10 to the power 3 to 10 to the power 5 Kelvin. Okay? Whereas you know that all these things have TC which are between 1 to 10 Kelvin. So even if you do, let's say 1 to 10, 1 to 20, even. So therefore his fluctuation in three-dimensional clean superconductor is a completely irrelevant energy scale. It's so high that it will excite so little of phase fluctuation that it really does not affect the superconducting properties at all. This is the reason why BCS theory was so immensely successful, even though it's not clear that BCS had actually a priori estimated this number and neglected it. Possibly they just did it based on a hunch, and later calculations showed the reason why it was. All right. So now a question for you guys. So you have been doing this course for a while, and you can see that J3D is so large that it is irrelevant. When do you think, or how do you think it can become relevant? I have missed something here. You can see that J3D or J depends essentially on two things: the coherence length, but it depends even more strongly because it's proportional to the coherence length, but it is inversely proportional to the penetration depth square. So when will this quantity, how can this quantity become relevant? So if this has to become relevant, then J3D has to drop drastically. And eventually it will really become relevant when it will become of the order of delta, or it will become maybe even smaller than delta. So you can see from the expression that if it has to become, if it has to reduce, then coherence length of course has to be small and penetration depth has to be large. Okay. Now from whatever you have learned, how can coherence length become small and penetration depth become large? Any idea? Penetration depth depends on what? Say, how can I, if I am given a material, what can I do to that? If I am given a superconductor, what can I do to the superconductor to increase its penetration depth or decrease its coherence length, and maybe do both of them simultaneously?
Introduce defects.
Yes, that is correct. But can you explain a little bit more? Godachand Das, dirty limit. Yes. But what does dirty limit mean? Explain a little bit. Godachand, are you there? Can you listen? Can you hear?
So maybe if the sample is dirty, so there will be scattering. So coherence length will be small. So that means after that length scale, there will be
Yeah,
the
that
phase
is,
coherence will be lost.
that's right. So if you, so coherence length, you know that the dirty limit coherence length, in the presence of defect, the coherence length is actually the BCS coherence length into the mean free path square root. So therefore, if I, no, pinning has nothing to do with it. Pinning is a completely different thing. We don't have magnetic field here, we don't have vortices. Okay, I'm responding to the comments that are coming in the chat box as well. Okay, so in the dirty limit, the coherence length will decrease, as I have explained to you before. And you know that if I put in more and more of disorder, the lambda, the penetration depth will increase. And this we have done in great detail from the sum rule. So if you have forgotten, just refresh your memory. So since we have, since you have with increase in disorder, if you put in point disorder, if you increase scattering of electrons, then you have the coherence length that comes down and the penetration depth that increases. And therefore, in disordered superconductors, you can have J that comes down drastically. It can come down drastically and it can come down actually so much that it becomes smaller than delta. Now we'll do much more of this as we go on. But keep this in mind that in the presence of disorder, J can reduce drastically. All right. So I think we can stop here. In the next, so now we know that we have just defined so far just the energy scale. We know that if J becomes small, then we will have phase fluctuations that will be important. But then we need to know, we know what happens with temperature, for example, when we had just quasi-particle excitation in BCS. You have the superconducting gap that reduces in a particular way. You had the penetration depth that has a particular variation that you have all calculated numerically. So now we will have to ask ourselves, what is the manifestation of phase fluctuation when it is significant? So what we will be taking up in the next class is what is the manifestation of phase fluctuations. Okay, in the meantime, I want you to calculate this superfluid stiffness for conventional superconductors. Convince yourself that it is actually very, very high. And then I will show you some data on what happens when you put in disorder. That's for the next class. Okay, so there is no class on Monday because Monday is a holiday. We have Guru Nanak Jayanti, and the next class will be on Wednesday. Any question here? So are you guys doing the work for the project? Have you started working for the project? Okay, I don't hear an answer, but I hope very much that it is yes. Okay, I have one answer. Good. So if you, I think tomorrow some of you have set up some discussion with Surajit. We can also have discussion in the next week during the class or after the class. And but get going. This is not something that you'll be able to do quickly at the end. So get going soon. All right. So let us end here and see you on Wednesday.